Last speaker for our first session is Antoine Ligier from the Graphics.
All right. So good morning, everyone. I'm Antoine from TechPlot Europe, also known as Genius Graphics. Today is our first participation in an SU2 conference. By our, I mean together with my colleague Lothar over there. And the topic for today is higher order elements that I will abbreviate as HO. So a first summary, we'll talk about visualization. I go quickly through the basics of higher order elements and the challenges that they pose in terms of visualization. And then we'll see how to tackle those for two specific cases, isosurfaces and surfaces. So quick reminder about higher order elements. So most of finite element methods assume linear variations along elements, along the edges, whereas higher order elements assume a non-linear variation along those edges. So it's typically a quadratic or higher polynomial function. The element geometry can also be curved, and that allows better solving, especially if your solver has better than second order accuracy. So why do we use higher order elements? It's typically for high vertical flows, transient simulation, and also aeroacoustics. So here, if you look at the upper left image, that's a wind turbine, and you can see a lot of vortices at the wing tip that interact in kind of a very complex manner with the vortices that are in the wake of the pylon. Also, at the right side of the slide, you see an aeroacoustic simulation of a nozzle. At the top is a visualization of that higher order. Sorry.
Checking something. For some reason, this isn't showing up for people online. That's good. I think you're good. Sorry,
Sure. So at the top, you see what it looks like if you treat it as a linear solution, linear elements, whereas the actual solution at the bottom is actually very different from what you would represent treating that as a linear set of elements. So here is a small quote from the CFD Vision 2030. That's a paper that is made by NASA that you've probably heard about. So just a quick quote, higher order methods will likely increase in utilization. Also currently the ability to visualize results from higher order simulation is highly inadequate. That basically means we need to come with new solutions to visualize those higher order elements to be able to accurately represent the simulation. A few challenges that comes with that. Together, the first thing is that you have various data formats, so that could be CGNS, VTU, and so on. And that means you need to change the internal representation of the data within the visualization software. You also need to have performant visualization without excess subdivision. I'll go into subdivision right after that, so if it's a bit obscure right now, just wait for a slide or two. And most algorithms currently work for linear elements. So whenever you visualize an isosurface, a slice, a contour, you always assume extrema at the node of your element, whereas it's not true for higher order elements. Same for streamlines, strict lines, particle passes, and even the shading of surfaces. So what is the idea with isosurface visualization? The idea is to reuse the existing linear algorithm and to apply them to higher order element. So basically the idea is to subdivide higher order elements within smaller elements, and you assume them linear. So you do that recursive subdivision until you get the desired accuracy. And at each time you interpolate, of course, the higher order solution using the basis function on your new sub-elements. TechPlot has a unique approach that is to use a selective subdivision algorithm. That means you just keep the sub-elements that contains your isosurface and discard all of the other ones. That turns out to be a huge reduction in terms of RAM and also CPU costs. So quick word on subdivision, I'm just taking the example of a tetrahedra. It's quite similar for other element types such as prisms, pyramids, hex, bricks, and so on. Here you have a quadratic tetrahedra. So it has 10 points, the 4 nodes and 6 points at the middle of the edges. And you can basically subdivide it, that means cutting it into 8 sub-tetrahedras. So the recursive subdivision will cut that tetrahedra within 8 smaller tetrahedras. Then you interpolate using the HO basic function on the new nodes that you put in the middle of each sub-edges. And then you do that again and again until you have the desired accuracy. So at each time step, you discard basically the elements that you don't need, that basically are the ones that do not contain the isosurface. Here is the example on a prism. So this is a single element, and you can see an isosurface that is a sphere. So it's an isosurface of radius with regards to a point. Here you can see first thing on the right that the prism is actually not a straight element, it's not linear, so the surfaces of the element are curved. The second thing is that using that subdivision algorithm, discarding the element turns out to use only 2,500 subtets out of a possible 650,000. It is not cheap to create 650,000 per element just to visualize an isosurface, and that's where that algorithm comes very handy. It's also true for other kind of elements. So this is one single higher order pyramid, and we subdivide it, keeping only 4,000 tets out of 1,400,000 by using the recursive subdivision. So here on the right, you just see the sub-elements that are kept and that are basically the ones that contain the isosurface. Same for a tetrahedra. So this time we are looking at different level of subdivision. On the upper left, you have the isosurface. If you assume your tetrahedra is a linear element, so you can see that very little triangle at the left, and then you subdivide it different. Well, you apply different level of subdivision, so first, second, third, and fourth. And you can see that at the fourth level of subdivision, you have only 8,500 elements that contain that isosurface that are kept, and all of the rest, that's about 650,000 that are discarded. So on a real case scenario, here we are looking at a 1 million quadratic elements simulation. That's from the HO code from Mr. Wang. And that's an isosurface of density. So at the very top, you see the isosurface without any level of subdivision. And at the bottom, you see 2 levels of subdivision. So you can see that the isosurface is more defined, I would say, at the lower level, and you get a better catching of its isosurface. Using those algorithms, you just end up with 1.5 million subtets instead of 113 millions. So in a real case scenario, you can create 1.5 million tets on your laptop or visualization node. 113 million is already an expensive operation, so that wasn't an option. Another thing is that 1 million P2 element is still relatively small. In a couple of years, we'll end up with a couple of tens or even hundreds of millions of elements, higher order, and that will end up in billions of elements if you subdivide them all. All right, that's also true for surfaces. So here we are looking at the leading edge of MC swing from Onera. At the left, you see the higher order elements treated as linear. So you see that the leading edge is blunt. And actually, after 3 levels of subdivisions, you would see that the curvature of the leading edge is accurately represented. So subdivision also works for surfaces. It's also quite straightforward. So for a triangle, you just cut it in 4 smaller triangles. All right, what's next? So Edwin van der Weijden from Twente University is currently working on the implementation in SU2 to get a higher order output directly to TechPlot format, written in parallel, so that should be very efficient. And we are currently I would say in early implementation, but that should come very soon. So you should be able to use that if you're using TechPlot already. And that's it for today. So if you have any question or if you want to have more details on those work, you can contact us, either myself, a.later@techplot.com, or Lothar, l.liebert@techplot.com as well. So thank you very much. And if you have any questions, I guess I went very fast, so it's either a longer break or a longer session of questions.
Let me come for questions.
Yep.
Or you prepare the coffee. This one. I do have a question.
Yeah.
What about the high-level implementation of Engine, which wasn't here? I don't think there was any presentation of that work. Do you know what the status is? How close it is that one to be
Well,
analyzed?
we've been in touch, I think, like 6 weeks ago, and I had holidays, so I could not really follow closely. But I know that Edwin implemented that. We have a library that that is used. He outputted already some data sets, but I think it's kind of a simplified version of SU2 that you are using for development, CCF or something like that. Okay, maybe. That's it, yeah. He actually sent us some data sets, but we haven't had the occasion to look into that yet. But I would say it's probably coming very soon. So
You like library is ready for
yes, you just plug your code to the library and it writes in parallel directly to a tech.file. file. So yep.
It seems to me like it's problem dependent quantity how many subdivisions you want.
Yes.
It's in one slide, 8,
Yeah.
64, 512, and 1024,
Yeah,
4,000 subcells per cell. So is there, based on the data, that's actually the data set, or is it able to propose for based on the maximum level, how many subdivisions it's going to do?
So as you just stated, it's very problem dependent. So by default, when you load the data set in TechDot, it treats everything as linear, so it's fast. And then it's up to you as the user to define the number of subdivisions you want. Typically, if you want 3 levels of subdivision, you need to do 2. So what typically people do is they go for the 2 levels of subdivisions and the third until they get the accuracy or the representation they want. So we leave it to the user. You can choose which level of subdivision. And the workflow is typically to go, level by level until you reach the accuracy that you want.
Is there a measure that's shown for accuracy, or is it more theoretical?
Yes. Well, there are some quantitative measurements. So, we have quantitative measurements, so you can, see how close you get to the actual solution. Here, for example, on a sphere, it's really easy to, say, analytic solution to that sphere surface. So you could just integrate the surface of that sphere to see where you reach something very close to the actual surface. It depends on, what level of accuracy you need for your.
Because it shows the solutions in handle very different. And I think there could be all kinds of AAs problems that you see as a solution that is drastically changes with more.
Well, yes and no. If you take that example, all the steps in the middle lower part are contained within the lower left parts that are contained within the upper left part. So you subdivide, so you refine, but you will not step out of your horizon surface will not move, it will just get a higher level of details in resolution. So it's, yeah. Does that answer your question?
Final question?
More about that. So we're here for the first time. So we've had a good relationship with them over the years. So welcome. You guys are here. So the idea is for people who want to discuss, technology in general. I know folks in the community are using it. Please take advantage of the opportunity. So thanks for coming.
Thank you.